Welcome to Maths with EJD. In this video, I'll be talking about the breadth first search traversal algorithm. So from the last video, right, you already said that traversal is basically visiting every node in a graph. And there are different techniques, different algorithms for doing that. In the previous video, we considered it depth first search algorithm, where you take a branch and visit all the nodes on that branch, and then you backtrack and visit every node you come across as you backtrack. But in the case of breadth first search, let's see what this is about. So, what is the breadth first search algorithm? So, that's the first thing we are considering. So, the breadth first search algorithm, BFS, is a graph traversal method, graph traversal method that explores all neighbors. It explores all neighbors of a node. So in this case, if you pick a node, you will explore all its neighbors before moving. Okay, all the neighbors of a node before moving to the next level. Okay. Unlike the other one that uses backtracking, this one uses what is called a queue-based approach. So it uses so the a breadth first search method uses a queue based a queue based I think I want to write that in big letters now. It uses a queue based approach. So it's all about queuing here. It uses a queue based approach. So no need to backtrack in this case. So you pick a node, visit all its neighbors before you move on. Whereas in the depth first search method, so you pick, in that case, you visit all the nodes on a branch, then you backtrack and visit the neighbors you had jumped in the process of visiting all the nodes on the branch you took initially. Okay, so let's look at the steps in uh, breadth breadth first search algorithm. So let's do that. Steps in breadth first search algorithm. So the first step is to start start at a specified node. Start at a specified node rather, at a specified node, or what you call a root. Okay. Two, you enqueue. We're talking about queue here, right? Enqueue the starting node. Enqueue the starting node. Enqueue the starting node and mark it as visited. Mark it as visited. Okay. So having done that, step three, you now dequeue a node. So having marked that first node as visited, then you now do what is called dequeuing. So you dequeue a node, process it, process it, and you process it and enqueue, enqueue all its unvisited nodes, all its unvisited nodes, enqueue all its unvisited nodes, all its unvisited nodes. Oh, sorry, all its unvisited neighbors, rather, all its unvisited neighbors. So step four is basically to repeat until the queue is empty. Okay. Four, repeat, repeat until the queue, repeat the queue, until the queue is empty. Okay. That is what is happening there. All right. So I'll take exactly the same examples I did. I used the for DFS, depth first search, for BFS, the breadth first search. So let's go. Example. So the first example you remember was A, then, so this is A, then we have B, we have C, then we had D and E. So D, E like this. So, and you remember that for breadth first search, for depth first search, we just did A to B, B to D, backtrack to E, backtrack to A, and then visit C, like that. But in this case now, the case, I mean, the approach is different. So just like we have listed already, you start at a specified node. Imagine you starting at A, okay? If you start at A, for instance, okay? Now, the next thing you're going to do is you enqueue the starting node and mark it as visited. So we have enqueued it. That's A. That's where we're starting from. And we have marked it as visited. So painting it in yellow means I have visited it already, right? So the next thing is to dequeue that node. You process it and enqueue all its unvisited neighbors. So now, now that I've visited A, so it has been, so you can now dequeue it and visit all its unvisited neighbors. So for A now, the neighbors of A are B. So you visit B and then you visit C. Those are the neighbors of A. Okay. Having done that, so see the order. You visit from A, you visit B, then that's one neighbor of A. Another neighbor of A is C. So it means you move from A to B, and then you go back to A and visit. So it's more like A is your anchor, your pivot. So from A you visit B. So you go back to A and visit C. So once that is done, then you come back to B. So look at the order. In fact, I think I should be writing down the order. So you move from A to B, then of course to C. You won't say you are going back to A because A is the anchor. So you visit C. After visiting C now, then of course you also mark as you visited B, right? You know, B has joined this, then you visit C. So having done that, then you now go back to B again. B is now the next in the queue. Since you visited B before, then you now visit the neighbors of B again. So from B, you can go to D. So you mark that as visited. So here you have D, and then you also come back and visit E, which is also a neighbor of B. Okay. So at the end of the day, you have visited all the nodes. So if those are five districts in a community, the BFS way of visiting is pick a node, visit all the neighbors. Then once you have exhausted all the neighbors, then for instance, if A still had another node, maybe say F attached to A, so you have to do A, B, C, F. Then now go to D, E like that. Okay, so that is depth first search. Whereas um that is breadth first search rather. Depth first search would have been A, B, D, E, C, but breadth first search is A, B, C, D, E, like that. Okay, that's one example. So let me take another example. The second example I took the other time, just to drive home the point. So let's look at that. Um, okay, yet another example. Okay, so imagine that you have one, two, three, four, five, six, and then we have seven and eight here. So there's an edge between nodes one and two. 2 and 3, 3 and 4. I mean 3 and 7, 7 and 8, and 1, 4, 4, 5, 2, 5, 5, 6, 3, 4. So this is exactly what we have. So you remember the other time, if you're going to use the depth first search. So you just go from 1 to 2, 2 to 3, 3 to 7, 7 to 8. Then you backtrack to 7, there's no neighbor. You backtrack to 3, there's a neighbor. So you go to 6. So that way you had 1, 2, 3, 7, 8, 6. Then you backtrack to 2 and visit 5. So 1, 2, 3, 7, 8, 6, 5. Then you backtrack to 1 and then visit 4. So that'll be 1, 2, 3, 7, 8, 6, 5, 4. So that is the depth first search approach. But for the breadth first search approach, we have another, it's a different algorithm. So the breadth first search approach, see how that proceeds. So of course, you queue, one is in the queue first. So of course, one is obviously the first place you go. So you have one. So the next thing is you visit all the neighbors of one before you move on to the next level. So the first neighbor of one is two. Okay. So you can travel to two and mark it as visited. And of course, you can update the path here, one, two. So, but you cannot go on because one still has another neighbor. That neighbor is four. So you come back to one and visit the other neighbor that has not been visited, which is four. Okay. So four now has not been visited. So the next thing after two is four. Now you can move on to two. So you can see two had been visited already, right? So you visit all the neighbors of two again now. Okay. So so two has a neighbor called three. So you mark three as visited, and then you update this as where had been the place that had been visited, and then two still has another neighbor. So the neighbor is five. Okay, so you mark this as visited now. That's so after three now, where we go is okay. Let me take that down. After three, we visit five. Okay. Now you go to three again. Now three has two neighbors. So the first neighbor of three is six. So you can go to town six if you are talking about towns or something or districts now. So you visit six. Okay. So after visiting six, I'm actually following the order. Okay. I'm following the numbering. So because I mean, if we follow what I've been doing before, I'll go to the right before coming down. But here I'm just following the numbering. So from five now, we now go to six. So after six, the next neighbor for three is actually seven. So we visit seven after six. So we update this to be 7. And lastly, of course, there's only one other neighbor to 7, which is 8. And that is the order we go like that. So we have this to be 8. So compare this now, this is the breadth first search where you pick a node and visit all its neighbors before you move on. So again, compare that with what we did before, the depth first search. So, that was there we're doing, okay, maybe I can shrink this. Okay. Okay. Okay, this isn't working. I want to show that. Okay. So for depth first search, right? What would have done would have been moving from one to two to three to seven to eight. Then we now come backtrack and move to six, backtrack, move to five, backtrack, and move to four. So compare the two, you see they are totally different. So breadth first search is 1, 2, 4, 3, 5, 6, 7, 8. But depth first search is 1, 2, 3, 7, 8, 6, 5, 4. Like that. So those are the two different algorithms. But of course, our focus in this particular video is on this one. Okay. It's on the breadth first search algorithm. That's our focus in this particular situation. So I just did the DFS to compare with that. Okay. As we prepare to draw this to a close, let's see some properties, some key characteristics of the breadth first search. Let's see that. Okay, let's see key characteristics of this. Okay. Um, Key characteristics of depth first search. Key characteristics. Key characteristics. Okay. So of course, just like before, we talked about time complexity. Time complexity is simply how long it takes for an algorithm to run based on the input into the system. Okay. That's what time complexity is about. And it is denoted using the big O, So you have O something. So it can be linear, it can be log linear, it can be quadratic and things like that. So in the case of depth first search approach, the time complexity was big O of V plus E. Interestingly, it's actually the same for the breadth first search algorithm. So it is big O of V plus E. Of course, V is vertex. V talk at the vertices and E at the edges. So it's so the time complexity for both algorithms seem to be the same. So that's about the time complexity. Then how about the space complexity? Interestingly, the space complexity is still the same as for depth first search. So complexity, space complexity. So we have big O of V. So, and that is due to the Q. So the other one was due to backtracking. So this one is due to the Q. Due to the due to the Q. Okay. So that's about the space complexity. How about the applications? In what cases do we use um the breadth first search algorithm? So applications now, the applications, okay. The first one is finding shortest paths in unweighted graphs. Finding shortest paths, finding shortest paths in unweighted graphs. Finding shortest paths in unweighted graphs. Then two, network broadcasting. Network broadcasting. Okay. And finally, we talk about identifying connected components. Since from each node, you want to visit all the neighbors, so you can easily identify, uh, you know, identifying connected components, identifying connected components like that. So with this, we come to the end of the breadth first search traversal algorithm. Don't forget, traversal is basically about how you can visit all the nodes of a particular graph, you know. So, and we have seen two different algorithms. We saw that for the depth first search, the approach is stack, which is implicit or explicit, and for breadth first search, it is queue. Then we talk about the exploration order. The exploration order in depth first search is deep first, then backtrack. So go down the line as much as possible, and then you begin to backtrack. But the breadth first search algorithm is level by level. Pick a node, visit all the neighbors, and move on like that. And the use case for depth first search, the use cases are anytime, anywhere you need backtracking or for cycle detection. And then for breadth first search, we have shortest path in unweighted graphs, like we said. Then the time complexity and the space complexity are the same. So the time complexity for both will be big O of V plus E, and the space complexity is big O of V. So of course, the reason is for the depth first search, the reason for the space complexity of O of V is recursion or stack, while for breadth first search, The reason is Q, and that is it. So the depth first search and breadth first search algorithms are foundational for solving many computational problems in fields like artificial intelligence, network analysis, and computer vision. So that's the end of this video. From the next video, I'll be talking about shortest root problems with different kinds of algorithms. So if you don't want to miss that, so you need to sign up to this channel and hit the notification bell so you can get alerted when those videos are uploaded. Then don't forget to comment so that I can know if you need me to teach a topic or solve a problem, or if you find a mistake in anything I've done, I can always rectify that maybe by me in the comment section. And then like and share so that more people can have access to this great content. Till I see you again, have a nice time. Bye.